For this video, we are going to solve a situation related to reinforced concrete design, in which, originally, only the details are given on the available related past board exam problem references, and not the figures shown on the right, which I included to better understand the given situation. From our situation, we are given a reinforced concrete beam, simply supported, has a span of 6 meters, carries a total uniform dead load of 20 kilonewtons per meter, and a live load of 36 kilonewtons located at the midspan. If we will cut our beam, say in this part, we can expose the rectangular cross-section of our reinforced concrete beam containing the 20 mm diameter reinforcing bars. As stated, this beam has a width of 300 mm, which is our B, and an effective depth of 500 mm, which is our D. From the four questions given at our situation, let's begin by solving the first question, which we are asked for the maximum factored moment. Let us bring back our 6-meter simply supported beam and the loadings applied. From strength of materials or theory of structures courses, the maximum moment is usually located at the point of zero shear. But instead of drawing the shear and moment diagram just to determine that point, we can instead investigate the figure and notice that we have asymmetrical loading, heavily pressing at the center. Hence, the maximum moment is located at the mid-span. Take note, we are finding for the maximum factored moment. Therefore, we should consider ultimate condition, which from our situation, we are given this load combination. Using this load combination, our ultimate load U would be the maximum factored moment MU equals 1.2 of the dead load, which would be the maximum moment due to our dead load, plus 1.6 of the live load, which would be the maximum moment due to our live load. From theory of structures, we have formulas for the maximum moment based on various cases and types of beams. From those formulas, we need two of them for this case, which are the maximum moment of a uniform load over the entire span of a simple or simply supported beam, and the maximum moment of a concentrated load at the midspan of a simple beam. Going back, our mu would then be equal to 1.2 of the maximum moment due to our dead load, which is WL squared over 8, plus 1.6 of the maximum moment due to our live load, which is PL over 4. Using the given values, mu would be 1.2 of W given as 20 times L squared, which would be 6 squared over 8, plus 1.6 of P given as 36 times L being 6 over 4. Solving for mu, we would have a value equal to 194.4 kilonewton meter. And this is the final answer for the first question. For the second question, we are asked for the required number of 20 mm diameter tension reinforcements. The conventional method for this case involves solving for the value of A, comparing it to A max to determine if the design should be singly or doubly reinforced, applying equilibrium to solve for the steel area, and only then can the required number of bars be solved. But for this video, I am going to introduce to you a 4-step process that can be faster and less tedious. Step 1 would be to solve for the maximum factored moment mu, which we just did a while ago for the first question, having a value of 194.4 kilonewton meter. Step 2 would be to solve for Rn, which is the coefficient of resisting moment, given by this formula. Using this formula, we will have Rn equal to mu being 194.4 times 10 raised to 6, because we need to convert mu from kilonewton meter to newton millimeter over phi b d squared. From our situation, phi is given as 0.9, b is given as 300 mm, so we will have times 300, and d is given as 500 mm, so we will have times 500 squared. Solving for Rn, we will have a value equal to 2.88. Step 3 would be to solve for ρ and compare ρ to ρ max and ρ mean? Rho is the reinforcement steel ratio given by this formula. Using this formula, we will have rho equal to 0.85 of F prime C, which is given as 21 megapascals from our situation, over Fy, which is also given at our situation being 420 megapascals, times the quantity 1 minus square root of 1 minus 2 Rn, which we just solved a while ago being 2.88, over 0.85 of F prime C, which is still 21. Solving for rho, we will get a value approximately equal to 0.00753. Rho max is the maximum reinforcement steel ratio, which at our case should be tension controlled, given by this formula. Using this formula, our raw max would be equal to 0.85 of F prime C, which is still 21, over Fy, which is also still 420, times beta 1. Our F prime C is 21 megapascals, which is less than 28 megapascals. For F prime C's less than 28 megapascals, the value for beta 1 is equal to 0.85. So we will have times 0.85 times 3 over 8 times dt over d. For this case, since we are designing, because we are finding for the required number of bars, let us assume single layer tension reinforcements. Doing so, for single layer, dt over d is simply equal to 1. So we will have times 1. Solving for the value of rho max, we will have a value approximately equal to 0.01355. Notice our rho max is still greater than rho. Therefore, our beam will be designed as singly reinforced. Rho mean is the minimum reinforcement steel ratio, which varies depending on the value of F prime C. The F prime C at our case is 21 megapascals, which is less than 31.36 megapascals. Therefore, the rho mean formula we will use is this. Using this formula, rho mean would be equal to 1.4 over Fy, which is still 420. Solving for the value of rho mean, we will get a value approximately equal to 0.00333. Notice that rho is greater than rho mean but is still less than rho max. Since the value of rho we computed a while ago exceeds the minimum but remains below the maximum, therefore that value is safe and should be the rho we must use. Step 4 would be to solve for n, which is the number of bars that can be calculated by simply dividing the total steel area, AS, by the area of a single bar or tension reinforcement, AB. Using this formula, N would be equal to AS, which is simply equal to rho BD, over AB simply being pi over 4 dB squared, since the cross-section of a reinforcing bar is usually circular. Using the given and computed values, we will then have rho being 0.007523 times B being 300 times D being 500 over pi over 4 dB being 20 mm. So we will have times 20 squared. Solving for the value of n, we will get a value approximately equal to 3.59. Since n is the number of bars required, we cannot round down to exactly 3 pieces because the requirement is calculated to be more than that, being 3.59 pieces. Therefore, we must round up our answer to 4 pieces. And this is the final answer for the second question. For the third question, we are asked for the width of the beam given a total depth, effective cover, and a steel ratio we must use. We can easily solve this question by simply reversing the process we just did a while ago for the second question. That is, step 1 would be to solve for rho, which at our case is already given being 0.008. Step 2 would be to solve for Rn. We can use the formula for Rn a while ago in the second question, but it would be much easier if we will use this another formula for Rn. Using this formula, Rn would be equal to Rho given as 0.008 times Fy, which is still 420, minus rho Fy squared. We can take the first term and simply square it over 1.7 of F prime C, which is still 21. Solving for Rn would give you a value approximately equal to 3.04. Step 3 would be to use mu from Rn. From the first formula presented at the second question, we can derive this formula for mu. Using this formula, mu should still be 194.4, the value we calculated at the first question, times 10 raised to 6 to convert mu from kilonewton meter to Newton meter, equal to phi given as zero point 0.9 from our situation times Rn, which we just calculated to be 3.04, times the width of the beam, B, which we are solving for this question, times D squared. If we will bring back the cross-section of our beam, this is the width B. This is the height or total depth H. This is the effective cover stated at our question, measured from the outer face of our concrete to the centroid of, in this case, the tension reinforcements. And this is the effective depth D. From this figure, we can see that the effective depth D is simply the total depth H given as 450 mm minus the effective cover given as 65 mm. Then square the difference. Solving for B would give you a value approximately equal to 479.36 mm, which we must round up to 480 mm since we are designing for a dimension of our beam. And this is the final answer for the third question. And now for the fourth or last question, we are asked for the total depth of the beam, given a width and the same effective cover and steel ratio. For this question, we can actually adapt the three-step process we just did for the last question. That is, step 1 would be to solve for rho, which will still be 0.008 because the same rho value is given for these two questions. Step 2 would be to solve for Rn, but since rho did not change, as well as the values for Fy and F prime C, therefore we will have the same solution from the last question. Hence, our value for Rn will still be approximately 3.04. Step 3 would be to solve for mu from Rn, which we will still use this formula that we just used for the last question. Using this formula, we will have mu, which should still be 194.4 times 10 raised to 6 to convert mu from kilonewton meter to Newton millimeter, equal to phi still being zero point 0.9 times Rn, which is 3.04 times B, which is given as 300 mm times D squared. Solving for D, we will get a value approximately equal to 486.66 mm. Based from our figure that shows the cross-section of our beam, the total depth H is simply equal to the effective depth T plus the effective cover EC. Using this formula, H would now be equal to D, which we just calculated to be 486.66 mm, plus EC, which is still given as 65 mm. Solving for H, we will get a value equal to 551.66 mm, which again should be rounded up to 560 mm since we are designing for a dimension of our beam. And this is the final answer for the fourth or last question. And here ends our video. Thank you for watching.